Imagine a ball rolling up a hill. You can picture it in your mind, right? If it doesn't have enough energy to reach the top, it rolls back down, right? That's what we expect to happen. That's common sense, and it's how the world works on a large scale. We see it every day in our physical world, but in the realm of atoms and particles, the rules of the game change. Things get a lot more interesting and complex. Welcome to the mind-bending world of quantum tunneling. Here, the impossible becomes possible. Quantum tunneling is a phenomenon where particles can pass through barriers even if they don't have enough energy to overcome them. It's like magic, but it's real. Imagine our ball suddenly appearing on the other side of the hill as if it had burrowed through. It defies our everyday logic. That's essentially what happens in the quantum world. And it has profound implications for our understanding of the universe. It challenges our perception of reality. This strange behavior is possible because in quantum mechanics, particles aren't just tiny balls. They have dual characteristics. They can also behave like waves spread out over space. This duality is key to understanding quantum phenomena. This wave-like nature allows them to leak through energy barriers even if it seems impossible. It's a fundamental aspect of quantum mechanics. Quantum tunneling isn't just a theoretical curiosity, it's a real phenomenon with practical applications. It plays a crucial role in many natural phenomena, from nuclear fusion in the sun to the way our electronic devices work. Without it, much of modern technology wouldn't exist. To understand quantum tunneling, we need to delve into the bizarre world of quantum mechanics. One of the key principles is wave-particle duality. This means that particles like electrons can behave both as particles with defined positions and as waves spread out over space. When a particle encounters a barrier, its wave function interacts with it. Instead of stopping abruptly at the barrier, the wave function can actually extend through it, albeit with a reduced amplitude. This means there's a probability, however small, that the particle can be found on the other side of the barrier. The probability of tunneling depends on the height and width of the barrier and the energy of the particle. A thinner barrier or a higher energy particle will result in a greater probability of tunneling. This counterintuitive behavior has been experimentally verified countless times and forms the basis for understanding a wide range of phenomena. The first hints of quantum tunneling emerged in the early 20th century. In 1928, George Gamow used the newly developed theory of quantum mechanics to explain alpha decay, a process where atomic nuclei spontaneously emit alpha particles, or helium nuclei. Gamow showed that alpha particles could tunnel through the energy barrier created by the strong nuclear force, which would normally confine them within the nucleus. This was a groundbreaking discovery, demonstrating the reality of quantum tunneling. Another crucial experiment, known as the Esaki diode experiment in the 1950s, demonstrated tunneling in semiconductors. Leo Esaki's invention of the tunnel diode, which exploits the wave nature of electrons, earned him the Nobel Prize in Physics in 1973. These early experiments, along with many others, solidified the concept of quantum tunneling and paved the way for its application in various fields. Quantum tunneling is not just a theoretical concept, it has profound implications for our technological world. One of the most significant applications is in transistors, the building blocks of modern electronics. Transistors control the flow of electricity in electronic devices and rely on quantum tunneling to function. Electrons tunnel through thin layers of insulating material, allowing for the precise control of electrical currents, forming the basis of computers, smartphones, and countless other devices. Beyond electronics, quantum tunneling plays a crucial role in nuclear fusion, the process that powers the sun. In the sun's core, hydrogen nuclei, which are positively charged and repel each other, overcome this repulsion by tunneling through the electrostatic barrier. This allows them to fuse and release tremendous amounts of energy. Understanding and harnessing quantum tunneling has revolutionized our technological landscape and continues to drive innovation in diverse fields. Section 5: Quantum tunneling in medicine, a new frontier in diagnosis and treatment. The medical field is also exploring the potential of quantum tunneling. One promising area is medical imaging. Researchers are developing new techniques that exploit tunneling to visualize biological molecules and processes at the nanoscale. For instance, scanning tunneling microscopes, or STMs, use tunneling to create high-resolution images of surfaces at the atomic level. These microscopes have revolutionized material science and are being adapted for biological applications. Another area of exploration is in the development of new drug delivery systems. Scientists are investigating ways to use nanoparticles that can tunnel through cell membranes to deliver drugs directly to targeted areas within the body. Quantum tunneling offers exciting possibilities for advancing medical diagnostics and treatment, potentially leading to more precise and effective healthcare interventions. Section 6. Scanning tunneling microscopes, seeing the unseeable. The invention of the scanning tunneling microscope, or STM, in the 1980s revolutionized our ability to visualize and manipulate matter at the atomic scale. This groundbreaking technology opened up new frontiers in science and engineering, allowing us to see the world in ways previously thought impossible. STMs rely on the principle of quantum tunneling to create images of surfaces with unprecedented resolution. This principle allows electrons to pass through a barrier that would be insurmountable in classical physics. An STM uses a sharp, conductive tip that is brought extremely close to the surface of a material. The precision required in positioning the tip is extraordinary, often within a fraction of a nanometer. A voltage is applied between the tip and the surface, and electrons can tunnel through the vacuum between them. This tunneling effect is the key to the STM's ability to image surfaces at such a fine scale. The tunneling current is extremely sensitive to the distance between the tip and the surface. Even the slightest change in distance can result in significant variations in the current. By scanning the tip across the surface and measuring the tunneling current, an STM can create a topographic map of the surface with atomic resolution, revealing the individual atoms and molecules that make up the material. This capability has provided unprecedented insights into the atomic structure of material. STMs have become indispensable tools in nanoscience and nanotechnology, enabling researchers to study and manipulate materials at the atomic level. Their impact on scientific research and technological development cannot be overstated. Section 7. Quantum biology. Can life itself utilize quantum tunneling? Quantum biology is an emerging field that explores the role of quantum mechanics in biological processes. It seeks to understand how the strange and often counterintuitive principles of quantum physics might influence the behavior of living organisms. While quantum effects are often associated with the microscopic world, there is growing evidence that they may also play a role in living organisms. This evidence is leading scientists to reconsider the boundaries between classical and quantum realms. One area of interest is photosynthesis, the process by which plants convert sunlight into chemical energy. This process is incredibly efficient, and researchers are investigating whether quantum mechanics might be the key to understanding this efficiency. Recent research suggests that quantum coherence, a phenomenon where quantum states can exist simultaneously, might be involved in the efficient transfer of energy during photosynthesis. This could mean that plants are using quantum effects to optimize their energy use. Another area where quantum tunneling might be relevant is in enzyme catalysis. Enzymes are crucial for speeding up chemical reactions in living organisms, making life as we know it possible. Enzymes are proteins that speed up chemical reactions in living organisms, and some scientists believe that tunneling might play a role in the transfer of protons or electrons during these reactions. This could provide a new understanding of how enzymes achieve their remarkable efficiency. While still in its early stages, quantum biology offers a fascinating glimpse into the potential interplay between the quantum world and the processes of life itself. As research progresses, we may uncover even more surprising ways in which quantum mechanics influences the living world. Section 8. The future of tunneling. From quantum computers to teleportation. Quantum tunneling continues to inspire new technological advancements and theoretical explorations. One of the most exciting areas of research is quantum computing. Quantum computers exploit the principles of quantum mechanics, including superposition and entanglement, to perform calculations that are impossible for classical computers. Tunneling plays a crucial role in some qubit designs. the basic unit of information in quantum computers. Another futuristic concept is quantum teleportation, the ability to transfer quantum information instantaneously between two distant locations. While not involving the physical transportation of matter, teleportation relies on the entanglement of particles, and tunneling can be used to create and manipulate these entangled states. While still in the realm of science fiction, quantum teleportation holds the potential to revolutionize communication and information processing in ways we can only begin to imagine. Section 9 Conclusion: The unending wonders of the quantum world. Quantum tunneling, once a mind-boggling concept, has become an integral part of our understanding of the universe and the technologies we rely on. From the heart of stars to the transistors in our smartphones, tunneling plays a vital role in shaping the world around us. As we delve deeper into the quantum realm, we continue to uncover new wonders and possibilities. The future of tunneling promises even more groundbreaking discoveries, pushing the boundaries of our imagination and leading us towards a deeper appreciation of the universe's elegant and often counterintuitive laws.